There was only the vastness of the unknown. Humanity stood at the edge of forests, at the shores of seas, at the boundaries of deserts, and wondered what lay beyond. To venture into these spaces without guidance was to risk becoming lost forever, swallowed by landscapes that all looked the same, where one tree resembled another, where oceans stretched endlessly in every direction, where sand dunes shifted and reformed with each wind. The world was immense and disorienting, and our ancestors needed a way to find their path through it. The first compass was not made by human hands. It was written in the sky, in the great celestial dome that turned above our heads each night. Ancient peoples, perhaps as far back as 40,000 years ago, learned to read the stars like a map spread across the heavens. They noticed that while most stars wheeled in great circles through the night, one star remained nearly fixed in place, anchored in the northern sky. We call it Polaris now, the North Star, though it hasn't always held this position and won't forever. But for the past several thousand years, this steady point in the sky has shown travelers which way was north, allowing them to orient themselves even in the darkest night, even in the most featureless terrain. But the stars could only guide those who traveled by night, and only when the sky was clear. Clouds, storms, daylight, all of these rendered the celestial compass useless. Ancient mariners hugging the coastlines of the Mediterranean and traversing the Indian Ocean developed other techniques. They learned to read the flight patterns of seabirds, which rarely ventured more than a day's flight from land. They studied the color and temperature of water, the types of seaweed floating on the surface, the shape and direction of waves. The Polynesians, those master navigators of the Pacific, learned to sense the subtle swells that radiated from distant islands, feeling through the hull of their canoes the way ocean currents bent and reflected around unseen land masses hundreds of miles away. Navigation was an art of attention, of reading 1,000 subtle signs woven into the fabric of sea and sky. Sometime around the 11th century CE in China, during the Song dynasty, someone made a discovery that would change navigation forever. They found that a certain type of iron-rich rock, when suspended freely or floated on water, would consistently align itself in a north-south direction. This rock was magnetite, also called lodestone, a naturally magnetic mineral that had been known to the ancient Greeks and others for centuries. The Greeks had named it after Magnesia, a region in Asia Minor where it was found. But the Chinese were the first to realize its profound practical application. This stone could show direction reliably and consistently, regardless of weather, time of day, or location. The earliest Chinese compasses were remarkably simple. A piece of lodestone would be carved into the shape of a spoon and placed on a smooth bronze plate marked with directions. The rounded bottom of the spoon allowed it to rotate freely, and the handle would invariably swing to point south. The Chinese traditionally oriented their maps with south at the top. These compass spoons, called south-pointing ladles, were used initially not for navigation but for divination and geomancy, the practice of feng shui, helping to orient buildings and graves in harmonious alignment with the Earth's energies. The magnetic compass was a spiritual tool before it became a navigational one. Chinese craftsmen soon developed more practical designs. They discovered that if you rubbed a steel needle against lodestone many times in the same direction, the needle itself would become magnetized, acquiring the same mysterious directional property. These magnetized needles could be floated on water in a bowl, suspended by a thread, or balanced on a pin, and they would align themselves north-south just as lodestone did. By the 11th century, Chinese navigators were using these magnetic needles aboard their ships, particularly for voyages across the South China Sea where clouds often obscured the stars and familiar landmarks disappeared beyond the horizon. The knowledge of this magnetic compass gradually spread westward, carried along the trade routes that connected China to the Middle East and Europe. Arab traders and navigators encountered the device and recognized its value immediately. By the late 12th century, accounts of magnetic compasses began appearing in the Islamic world, where scholars wrote about this remarkable needle that always knew which way was north. The Arabic word for compass, basola, would eventually evolve into various European terms for the instrument. Europeans received the compass sometime in the late 12th or early 13th century, though the exact route of transmission remains debated by historians. What is certain is that by 1190, European sailors were using magnetic compasses, and the device spread rapidly throughout the Mediterranean and Atlantic seafaring communities. Early European compasses consisted of a magnetized needle mounted on a card marked with directions, the whole assembly floating in a bowl of water or oil to keep it level on a rocking ship. For the first time, mariners could determine direction even when sun and stars were hidden, even in the midst of storms, even in the featureless gray of foggy seas. This simple device, a magnetized needle that pointed north, may have been the single most important navigational invention in human history. Before the compass, sailors rarely ventured far from coastlines, using landmarks to guide them. Long ocean crossings were perilous not just because of storms and supplies, but because of the very real possibility of becoming hopelessly lost. With the compass, the open ocean became navigable. Ships could maintain course across hundreds of miles of empty water, confident in their direction even when they couldn't see land for days or weeks. The psychological impact was perhaps as significant as the practical one. The compass gave sailors confidence, a sense of control over the vast and chaotic ocean. They carried with them a tool that connected them to something fundamental in nature, an invisible force that pervaded the entire world. That little needle, trembling and then settling into alignment, was proof that order existed even in the midst of chaos, that direction could be found even when all other references were lost. The compass transformed the ocean from an incomprehensible void into a space that could be crossed, mapped, and mastered. Yet even as Europeans embraced the magnetic compass, they didn't understand why it worked. The concept of magnetic fields, of invisible lines of force permeating space, wouldn't be developed for centuries. Medieval sailors knew only that the needle pointed north through some mysterious property of lodestone and magnetized iron. Some thought the compass needle was attracted to the North Star itself, drawn by stellar influence. Others believed vast mountains of magnetic rock existed at the Earth's poles, pulling the needle toward them. These explanations were wrong, but they didn't need to be right for the compass to work. The device functioned perfectly well even when its users misunderstood the principles behind it. As you rest now, breathing slowly and deeply, imagine the wonder those early navigators must have felt, watching that needle swing into alignment, pointing always toward the same direction no matter how many times they turned the compass, no matter where their ship sailed. In their hands they held a connection to forces invisible yet utterly reliable, a guide that never slept, never tired, never lost its way. Let that image settle into your mind. The steady needle, the cardinal directions, the sense of orientation in a disorienting world, and allow yourself to drift, centered and calm, as reliably oriented toward rest as that ancient needle was toward the north. As the magnetic compass spread across the seafaring world in the 13th and 14th centuries, craftsmen began to refine and improve the design, transforming it from a simple floating needle into an increasingly sophisticated instrument. Italian compass makers, particularly those in the maritime republics of Genoa and Amalfi, became renowned for their craftsmanship. They developed what became known as the dry compass, where instead of floating in liquid, the magnetized needle was mounted beneath a circular card marked with directions, and the entire assembly pivoted on a pin. This design was more robust, less likely to spill in rough seas, and could be read more quickly by a helmsman trying to maintain course through rolling waves. These compass cards became works of art as well as navigation tools. The 32 points of the compass rose emerged during this period, dividing the circle not just into the 4 cardinal directions, north, south, east, and west, but into increasingly fine subdivisions. Between north and east lay northeast, and between north and northeast lay north-northeast, and so on, creating a vocabulary of direction precise enough for the demands of ocean navigation. The compass rose was often elaborately decorated, with the north point marked by a fleur-de-lis and the east point by a cross, reflecting the Christian culture of medieval Europe and serving as a mnemonic. The cross marked the direction of Jerusalem, the Holy Land. These beautiful instruments, housed in wooden or brass boxes, became treasured possessions, sometimes passed down through generations of sea captains. But as mariners ventured farther from European waters, they began to notice something troubling about their trusted compass. In different parts of the world, the needle didn't point exactly north. In some locations, it pointed slightly east of true north, in others slightly west. This deviation, which sailors called variation or declination, was deeply puzzling and concerning. If the compass couldn't be trusted to point north consistently, how could it be relied upon for navigation? Some sailors thought their compasses had become corrupted, that the magnetism had somehow gone wrong. Others suspected that local deposits of magnetic rock in the earth were pulling the needle off course. The first person to systematically study and document this magnetic variation was Christopher Columbus. During his voyages across the Atlantic in the 1490s, Columbus carefully noted the compass readings and compared them to his calculations of true north based on celestial observations. On his first voyage in 1492, he observed that as he sailed westward, the compass variation changed. The needle pointed east of north when he was near Europe, but as he crossed the ocean, there came a point where the compass pointed directly to true north, and farther west it began pointing west of north. Columbus kept this observation secret from his crew, fearing it would alarm them, but he recorded it in his log. This was the first recorded observation of the agonic line, an imaginary line on Earth's surface where magnetic north and true north align. The reality of magnetic variation posed a significant problem for navigation. A ship sailing on a compass bearing that was off by even a few degrees would, over hundreds of miles, end up far from its intended destination. Throughout the 16th century, as European ships ranged ever farther across the globe, navigators compiled tables of magnetic variation for different locations, trying to map this invisible and perplexing property of Earth's magnetic field. What they couldn't have known was that magnetic variation wasn't just different in different places. It was also changing over time. The Earth's magnetic field is generated by currents in the molten iron of the planet's outer core, and these currents shift and flow, causing the magnetic poles to wander and the patterns of variation to evolve across decades and centuries. In 1600, an English physician and natural philosopher named William Gilbert published a revolutionary book called De Magnete, on the magnet, which was the first comprehensive scientific study of magnetism. Gilbert conducted hundreds of experiments with lodestones and magnetized needles, and from these observations, he reached a stunning conclusion. The Earth itself was a giant magnet. This was a profound insight, explaining for the first time why compass needles pointed north. They weren't being drawn to the North Star or attracted to polar mountains. They were aligning with the Earth's own magnetic field, responding to the planet itself. Gilbert even constructed a small sphere of lodestone, which he called a terrella or little Earth, and demonstrated that a compass needle brought near it behaved exactly as compasses did on Earth's surface, proving his theory through experimental demonstration. Gilbert's work transformed the compass from a mysterious device into an understood scientific instrument, though many questions remained. He couldn't explain why the magnetic poles didn't coincide with the geographic poles, or why magnetic variation existed and changed over time. But he had revealed the fundamental principle. Magnetism was a property of Earth itself, a planetary phenomenon. This knowledge elevated the status of the compass from a practical tool to an object of scientific inquiry, worthy of study by the greatest minds of the age. As the age of exploration continued through the 16th and 17th centuries, the compass became the primary means of maintaining direction during long ocean voyages. But navigators needed more than just direction. They also needed to know their position on the vast blank canvas of the ocean. Determining latitude, your north-south position, was relatively straightforward using instruments like the astrolabe or quadrant to measure the angle of the sun or stars above the horizon. But longitude, your east-west position, remained maddeningly difficult to calculate. The compass alone couldn't solve this problem, but it was essential for a technique called dead reckoning, where navigators would estimate their position by keeping careful track of the ship's speed and direction over time. A navigator practicing dead reckoning would use the compass to maintain a steady course, while simultaneously estimating the ship's speed by various means, tossing a piece of wood overboard and timing how long the ship took to pass it, or later, using a device called a chip log, where a wooden board attached to a rope with knots tied at regular intervals would be thrown overboard, and the number of knots that played out in a fixed time gave the ship's speed in knots, a term we still use today. By combining compass direction with speed estimates and accounting for currents and drift, a skilled navigator could calculate roughly where the ship had traveled. This was never perfectly accurate. Errors accumulated with every hour at sea, but it was the best method available for centuries. The reliance on dead reckoning made the compass absolutely critical. If the compass was inaccurate, every calculation built upon its readings would be wrong, and the ship could end up far from its intended course. Ships' compasses were treated with almost religious reverence, protected from damage, checked and rechecked. Sailors developed superstitions about compasses, believing that certain actions might disturb their magnetism. Some thought garlic or onions near a compass could kill its magnetic properties, or that lightning strikes could reverse its polarity. While these beliefs were unfounded, they reflected the deep dependence mariners had developed on this single instrument. In an age where ships might sail for months without sighting land, where the horizon looked the same in every direction, that trembling needle was often the only thing standing between a successful voyage and complete disorientation. Breathe deeply now and imagine yourself on the deck of one of those ships, weeks from any shore, surrounded by endless water beneath endless sky. The world rocks gently beneath your feet, the compass steady in its housing, its needle holding true. There is something deeply calming about that constancy, that reliable orientation even in the midst of vastness and uncertainty. Let your mind settle like that compass needle, finding its natural alignment, pointing steadily toward rest, toward peace, toward the quiet center that remains constant no matter how the world around you moves. The 18th century brought new sophistication to compass design, driven by the increasing complexity of maritime commerce and naval warfare. Ships were growing larger, carrying more valuable cargoes across longer distances, and the need for accurate navigation had never been greater. One persistent problem with ship compasses was that as vessels were built with more iron components, iron nails, bolts, cannons, anchors, these metal objects interfered with the compass needle, creating what sailors called deviation. Unlike variation, which was caused by Earth's magnetic field and remained constant for a given location, deviation was specific to each ship, caused by the magnetic influence of the vessel's own iron. A compass might read accurately on land, but once installed aboard a particular ship, it would point in a slightly different direction. In 1775, a British instrument maker named Gowan Knight developed an improved method of magnetizing compass needles that made them more powerful and stable. Rather than using a single straight needle, Knight created compound needles using multiple thin strips of steel, carefully magnetized and bound together. These stronger magnets were less susceptible to the disturbing influences of a ship's iron. Knight's innovations were adopted by the Royal Navy, giving British ships a navigational advantage during an era when naval power directly translated to imperial power. The compass had become not just a tool of exploration and commerce, but a weapon of war. The nation with the best compasses could navigate more accurately, position their fleets more precisely, and maintain course through conditions that left enemy vessels groping blindly. But even the best compasses of the 18th century suffered from mechanical limitations. The card that showed directions would stick and hesitate, especially in the damp conditions common at sea. The pivots would wear down over time, causing the compass to become sluggish and unreliable. In 1876, Lord Kelvin, William Thomson, one of the great physicists of the Victorian era and the man after whom the absolute temperature scale is named, turned his attention to these problems. Kelvin had been consulting with shipping companies and had seen firsthand how inadequate ship compasses were, particularly on the new iron and steel vessels that were replacing wooden ships. Kelvin designed a revolutionary liquid compass that housed the magnetized needles and compass card in a bowl filled with a mixture of alcohol and water. This liquid served multiple purposes. It damped the oscillations of the compass card, preventing it from swinging wildly in rough seas. It reduced friction on the pivot point, making the compass more responsive, and it helped support the weight of the card, reducing wear on the delicate pivot. Kelvin's compass also used very thin, lightweight needles, as many as 32 of them, arranged in sets around the card, which were more sensitive to Earth's magnetic field than the heavier designs used previously. The result was a compass that was quick to settle, accurate, and reliable even in the harsh conditions of ocean navigation. The Kelvin compass was so superior to earlier designs that it became the standard for maritime navigation almost immediately. By the 1880s, virtually every significant ship in the world was equipped with a Kelvin compass, and the basic design would remain in use for over a century. Kelvin had transformed the compass from a somewhat crude directional indicator into a precision instrument worthy of the industrial age. It's worth noting that Kelvin made substantial personal profit from his invention. He held the patents and manufactured the compasses through his own company. Science and commerce had become intertwined, with improvements in navigation technology driven as much by market forces as by pure curiosity. Around the same time that Kelvin was perfecting the liquid compass, other scientists and navigators were working on the problem of deviation, that troublesome magnetic interference from a ship's own iron. In 1838, a British naval officer and astronomer named George Bid-del-Airy had developed a method for compensating for deviation using carefully placed magnets and iron spheres positioned around the compass. By analyzing how a particular ship affected its compass and then strategically placing correcting magnets, the compass could be adjusted to read accurately despite the ship's magnetic field. This process, called swinging the ship, involved sailing the vessel in a complete circle, measuring the compass error at regular intervals, and then making adjustments to minimize these errors. The mathematics behind compass compensation were sophisticated, and ships began to carry specialized compass adjusters, experts who understood both magnetic theory and practical seamanship, and who could tune a compass to a particular vessel. By the late 19th century, compass adjustment had become a precise science, with detailed tables and procedures. A well-adjusted compass on a steel ship could be nearly as accurate as one on a wooden vessel, removing what might have been an insurmountable obstacle to the transition from wood to metal shipbuilding. It's remarkable to think that the great steel steamships that crossed the oceans in the early 20th century Massive vessels weighing thousands of tons, constructed entirely of iron and steel, could still navigate using magnetic compasses, devices that fundamentally relied on the same principle as the floating lodestone needles of 11th century China. As the 20th century arrived, a new challenge emerged for the compass: aviation. The first powered aircraft flights occurred in 1903, and within a decade, aviators were attempting longer flights, including attempts to cross large bodies of water and unfamiliar terrain. But aircraft presented unique problems for compass use. Unlike ships, which moved relatively slowly and maintained a fairly steady platform, aircraft could bank sharply, climb and dive, and accelerate rapidly. The liquid compasses that worked so well at sea would slosh and tumble, becoming unreadable during maneuvers. The magnetic field inside an aircraft's metal fuselage, with its engine and electrical systems, created severe deviation problems. Early aviators often had to navigate by visual landmarks alone, or by following roads and railways when they could see them. The solution came in 1927, when a former British Royal Flying Corps pilot named Leslie Francis Smith invented the directional gyroscope, which became known as the gyrocompass when adapted for aircraft use. This device used a rapidly spinning wheel, or gyroscope, that resisted changes in orientation due to its angular momentum. Once aligned with true north, the gyroscope would maintain that orientation regardless of the aircraft's movements. Unlike magnetic compasses, gyroscopes weren't affected by metal, electrical systems, or magnetic variation. They pointed to true north, not magnetic north, eliminating one entire source of navigation error. The gyrocompass required electrical power to keep the gyroscope spinning, but it transformed aviation navigation, making it possible for aircraft to maintain course even through clouds, at night, or during complex maneuvers. Interestingly, gyrocompasses had been developed earlier for ships, with the first practical marine gyrocompass invented by Hermann Anschutz Kempfer in Germany in 1908 and improved by Elmer Sperry in the United States. These ship gyrocompasses were large, complex devices that used the rotation of the Earth itself to maintain orientation. But they were too large and power-hungry for early aircraft. The aviation gyrocompass was a miniaturized version, and its development represented a shift in navigation technology, from passive devices that sensed natural forces like magnetism to active systems that maintained orientation through mechanical means. Yet, for all the sophistication of gyrocompasses, the simple magnetic compass remained essential, serving as a backup and reference. Even today, with GPS and inertial navigation systems, aircraft still carry magnetic compasses. They're required emergency equipment, simple and reliable, needing no power source, immune to electronic failure. The magnetic compass has proven to be one of the most enduring technologies in human history, a device invented nearly 1,000 years ago that remains relevant in the 21st century, an elegant solution to the fundamental problem of orientation that no amount of modern technology has rendered obsolete. Let your breathing slow now, becoming as steady as a compass needle settling into alignment. Feel yourself oriented, centered, pointing toward rest like that ancient needle pointing toward north. The world may spin and turn around you, but you remain constant, held by forces deeper than thought, more fundamental than worry. Close your eyes and drift, aligned with that invisible field that runs through all things, that connects you to the planet beneath you, to the quiet center where all direction begins. As we move deeper into the 20th century, the story of the compass becomes intertwined with humanity's growing understanding of Earth's magnetic field itself, that invisible force that had guided travelers for nearly a millennium without being truly understood. Scientists had long known that Earth's magnetic field existed and that it wasn't perfectly aligned with the geographic poles. The magnetic North Pole, the point toward which compass needles actually point, was located in northern Canada, hundreds of miles from the true North Pole. But in the early 1900s, researchers made a startling discovery by examining rocks and ancient pottery. When certain rocks form from molten lava, or when clay is fired in a kiln, tiny magnetic particles within them align with Earth's magnetic field at that moment, like microscopic compass needles frozen in place. By studying rocks of different ages, geologists discovered something extraordinary. The direction of magnetization in ancient rocks didn't match the current magnetic field. Even more astonishing, some rocks showed magnetization pointing in completely the opposite direction, as if north and south had been reversed. At first, Scientists thought these rocks must have somehow flipped over or been disturbed, but the pattern was too consistent, too widespread. By the 1960s, the evidence had become overwhelming. Earth's magnetic field periodically reverses itself, with magnetic north and south switching places. These magnetic reversals, or geomagnetic reversals as scientists call them, occur irregularly throughout Earth's history. The last one happened about 780,000 years ago, when early humans were still using stone tools and the compass hadn't yet been invented. The process isn't instantaneous. A reversal takes thousands of years to complete, during which the magnetic field weakens and becomes chaotic, with multiple magnetic poles wandering across the planet's surface before settling into a new, reversed configuration. During these transition periods, compasses would become increasingly unreliable, their needles wavering and uncertain. Fortunately for navigation, reversals are rare on human timescales, occurring roughly every few 100,000 years on average, though the intervals vary greatly. This discovery of magnetic reversals led to a revolution in geology. Scientists realized that the ocean floor, formed by volcanic activity at mid-ocean ridges, recorded these reversals in stripes of alternating magnetic polarity. As new seafloor spread outward from the ridges, it preserved a record of Earth's magnetic history stretching back millions of years. This evidence became a cornerstone of plate tectonics theory, helping to prove that continents drift and ocean floors spread, transforming our understanding of Earth itself. The humble compass, that tool of navigation, had inadvertently provided the key to unlocking one of the great mysteries of planetary science. While scientists were decoding Earth's magnetic past, military necessity during World War II drove rapid advances in practical navigation technology. Submarines posed a particular challenge. Magnetic compasses were unreliable underwater, affected by the steel hull and the vessel's electrical systems, and celestial navigation was impossible when submerged. The answer came through improved gyrocompasses and the development of inertial navigation systems. These systems used accelerometers to measure every change in velocity and gyroscopes to track every change in direction, allowing a computer to calculate the vessel's position through dead reckoning, but with the precision impossible for human navigators. Starting from a known position, an inertial system could track a submarine's movements through the ocean depths, maintaining an accurate position fix for days without any external reference. Inertial navigation represented a philosophical shift in how we thought about finding our way. For thousands of years, navigation had relied on external references: the sun, stars, landmarks, or the magnetic field. Inertial navigation was entirely self-contained, relying only on the vessel's own movements and the laws of physics. A submarine using inertial navigation could travel beneath the polar ice cap, where magnetic compasses spun uselessly and no stars could be seen, and still know precisely where it was. This technology, developed for military purposes, would eventually find civilian applications in commercial aircraft and spacecraft, allowing navigation in any environment, no matter how hostile or featureless. The next great revolution in navigation came not from improving the compass, but from transcending it entirely. In the 1970s, the United States military began deploying a constellation of satellites that would become the Global Positioning System, or GPS. The concept was elegant. Satellites orbiting Earth would continuously broadcast radio signals containing precise timing information and their own orbital positions. A receiver on the ground, listening to signals from multiple satellites, could calculate its exact position by measuring how long the signals took to arrive, essentially using the speed of light as a cosmic measuring stick. With signals from at least 4 satellites, a GPS receiver could determine its latitude, longitude, and altitude to within a few meters. GPS became fully operational in 1995, and its impact on navigation was revolutionary. For the first time in human history, anyone with a small electronic device could know their exact position anywhere on Earth's surface, instantly and continuously, without needing any skill in navigation, without reading stars or magnetic fields or landmarks. The GPS receiver performed calculations that would have taken a skilled navigator hours, and it did them in fractions of a second. Ships no longer needed to carefully plot their course on charts. Their position was continuously displayed on electronic screens. Aircraft could navigate with unprecedented precision, following routes to within meters. Even ordinary people in cars or hiking in wilderness could navigate with confidence that would have amazed professional navigators of earlier eras. Yet GPS had limitations that became apparent over time. The system relied on satellites, and satellite signals are weak. They can be blocked by buildings, mountains, or even dense tree canopy. Underground, underwater, or indoors, GPS often fails. The signals can be jammed or spoofed, creating false positions. In war or during system failures, GPS could become unavailable. And so, remarkably, the magnetic compass, that ancient device invented in China 1,000 years ago, remains relevant even in the GPS era. Ships still carry magnetic compasses as backup navigation tools. Hikers pack small compasses alongside their GPS devices. Military forces train soldiers in compass navigation as an essential skill for when electronics fail. The persistence of the magnetic compass speaks to something profound about good design. Unlike GPS, which requires satellites, ground stations, atomic clocks, and continuous electrical power, the magnetic compass needs nothing but a magnetized needle and a pivot. It cannot be jammed, cannot run out of batteries, cannot lose signal. It responds to a fundamental force of nature, Earth's magnetic field, that has existed for billions of years and will continue long after our technological civilization has passed. The compass is passive, eternal, elegant in its simplicity. It represents a different philosophy of technology, not dominating nature with complex systems, but aligning with nature, sensing and following forces that already exist. This philosophical dimension extends to how we think about orientation and direction in our lives. The compass teaches us that there are constant reference points, stable forces we can align ourselves with, even when everything else seems uncertain. Just as a compass needle always finds north, perhaps we too have internal reference points, values, principles, purposes, that can orient us when we feel lost. The compass is a teacher as well as a tool, reminding us that steadiness and constancy have value, that simple solutions often endure longer than complex ones, that some truths are written into the fabric of reality itself. Rest now in this thought. Somewhere deep in the earth, currents of molten iron spiral and flow, generating the magnetic field that encompasses our entire planet, that reaches out into space, that shields us from solar radiation and cosmic rays, and that also, quietly, persistently, orients every compass needle that has ever been magnetized. You are held within this field, part of a planetary system far larger than yourself, connected to forces ancient and ongoing. Let yourself settle into this connection, this orientation, this alignment with something fundamental and enduring. Breathe slowly and feel yourself pointing, like a compass needle, toward your own true north, toward rest, toward peace, toward the quiet center where all seeking ends. While GPS transformed navigation on Earth's surface, humanity was simultaneously pushing outward into space, where the magnetic compass became utterly useless. Beyond Earth's atmosphere, there is no magnetic field to guide a needle, no north or south in the conventional sense. The first astronauts and cosmonauts venturing into orbit in the 1960s needed entirely new methods of orientation. In the vacuum of space, navigation relied on gyroscopes, star trackers that identified constellations and calculated orientation from stellar positions. and accelerometers that measured every tiny change in velocity. The Apollo missions to the Moon carried sophisticated guidance computers that were, for their time, marvels of miniaturization. Though less powerful than a modern smartphone, they were sufficient to navigate across 250,000 miles of void. Space navigation revealed just how Earth-centric our concepts of direction had always been. In orbit, there is no up or down, no north or south. Astronauts had to learn to think in terms of vectors and coordinate systems, of velocity changes and orbital mechanics. The International Space Station, orbiting Earth 16 times per day, experiences a constantly changing relationship to magnetic north as it circles the planet. Its orientation is maintained not by any compass but by momentum wheels and gyroscopes, by computer calculations and thruster firings. Yet even in space, Earth's magnetic field remains relevant. Satellites in low Earth orbit experience slight drag from residual atmosphere and subtle torques from Earth's magnetic field pulling on their metal structures, effects that must be compensated for to maintain proper orientation. Back on Earth, scientists made another remarkable discovery about the magnetic sense that compasses exploit. In the 1970s, researchers found that many animals possess an internal biological compass, allowing them to detect Earth's magnetic field and use it for navigation. Homing pigeons, those birds that can find their way home across hundreds of miles of unfamiliar territory, have magnetite crystals in their beaks that function as natural compass needles, connected to specialized nerve cells that allow the birds to sense magnetic direction. Sea turtles, born on beaches, swim out into the ocean and spend years wandering across vast distances before somehow finding their way back to the very beach where they hatched. They navigate using Earth's magnetic field, sensing not just direction but also the subtle variations in field strength that create a kind of magnetic map. Even more astonishing, researchers discovered that some bacteria contain chains of magnetite crystals that cause them to orient along magnetic field lines, a phenomenon called magnetotaxis. These magnetotactic bacteria, found in aquatic sediments worldwide, are essentially living compasses, using Earth's magnetic field to navigate toward their preferred depth in water or mud. This suggests that the ability to sense magnetic fields may have evolved very early in life's history, perhaps even before the Cambrian explosion over 500 million years ago. Humans, as far as we know, lack this magnetic sense. We are among the relatively few creatures that needed to invent an artificial compass because we couldn't feel Earth's magnetic field naturally. The compass is our technological compensation for a biological ability that many other species possess innately. The discovery of biological magnetoreption opened new questions about animal migration, those epic journeys that have puzzled naturalists for centuries. Monarch butterflies travel thousands of miles from North America to specific groves of trees in Mexico where their great-great-grandparents overwintered, trees they themselves have never seen. Arctic terns fly from pole to pole each year, covering over 40,000 miles, experiencing 2 summers annually and seeing more daylight than any other creature. Scientists now understand that many migratory species use multiple navigation cues: the sun's position, star patterns, landscape features, and Earth's magnetic field, creating redundant navigation systems of remarkable sophistication. The magnetic sense serves as a reliable backup when other cues are unavailable, functioning like an internal compass that never needs calibration. In the early 21st century, compass technology took an unexpected turn with the development of quantum compasses. These exotic devices exploit quantum mechanical effects to detect extremely subtle variations in magnetic fields. Unlike traditional compasses that simply align with Earth's field, quantum magnetometers can map the field with extraordinary precision, detecting anomalies caused by underground ore deposits, archaeological remains, or submerged submarines. Some quantum compasses use atoms cooled to temperatures near absolute zero, where quantum effects become pronounced, allowing measurements of magnetic fields billions of times weaker than Earth's. Others employ diamond crystals with specific defects that act as quantum sensors, their fluorescence changing in response to magnetic fields. These quantum compasses represent the cutting edge of navigation technology, but they also serve purposes far beyond simply finding direction. Geologists use them to map underground structures, searching for mineral deposits or oil reserves. Archaeologists employ quantum magnetometers to detect buried ruins without excavation, revealing the foundations of ancient buildings beneath farmers' fields. Medical researchers are developing quantum magnetic sensors to map brain activity with unprecedented precision, detecting the minute magnetic fields generated by neurons firing. The compass, which began as a simple tool for finding north, has evolved into an instrument for exploring the invisible architecture of reality itself, sensing magnetic fields that pervade everything from the Earth's interior to the human brain. Yet even as quantum physics was being applied to compass technology, many cultures around the world maintained traditional navigation methods that predated the magnetic compass entirely. The Pacific Islanders of Polynesia, Micronesia, and Melanesia preserved navigation techniques passed down through generations, techniques that allowed their ancestors to colonize islands across millions of square miles of ocean using only outrigger canoes. These master navigators, called wayfinders, used a holistic approach to navigation, integrating observations of stars, wave patterns, wind directions, cloud formations, bird behavior, and ocean color into a comprehensive awareness of their position and direction. They memorized star paths, the rising and setting points of stars throughout the year, creating a celestial compass that required no instrument. Perhaps most remarkably, Pacific navigators could sense wave patterns in ways that seem almost supernatural to those unfamiliar with the technique. Ocean swells travel thousands of miles from their origin, and when they encounter islands, they reflect and refract, creating complex interference patterns. A skilled wayfinder, lying in the bottom of a canoe and feeling the motion of swells through the hull, could detect these patterns and navigate toward islands beyond the horizon, islands they couldn't possibly see. This wasn't mysticism but profound empirical knowledge, accumulated through generations of observation and refined through natural selection. Navigators who couldn't find their way home didn't pass on their techniques. In recent decades, there's been a revival of traditional wayfinding, with organizations like the Polynesian Voyaging Society building replica voyaging canoes and training new generations in these ancient skills, demonstrating that GPS and magnetic compasses, for all their precision, are not the only ways to find direction across the ocean. This persistence of traditional navigation alongside modern technology reminds us that there are multiple ways of knowing, multiple forms of intelligence. The magnetic compass represents one approach, using a tool to sense a natural phenomenon invisible to human perception. GPS represents another, using technology to create an artificial reference system independent of natural cues. Traditional wayfinding represents yet another, training human perception and memory to integrate countless subtle environmental signals into navigational awareness. Each approach has strengths and limitations, and perhaps wisdom lies not in abandoning older methods for newer ones, but in understanding when each is most appropriate. As you rest now, consider the many ways we orient ourselves in the world. We use tools and instruments, technology and tradition, inner sense and outer reference. Sometimes we navigate by stars we can see, sometimes by magnetic fields we cannot, sometimes by satellites orbiting overhead, sometimes by knowledge carried in memory and culture. All of these are forms of wayfinding, methods of determining where we are and where we're going. And perhaps the deepest navigation is internal, finding our way not through space but through life, orienting ourselves not by north and south but by meaning and purpose, by values and relationships, by the quiet internal compass that points us toward what truly matters. Let your breathing deepen and slow. You need no compass now, no GPS, no stars. In this moment, there is nowhere you need to go, no direction to maintain. You are exactly where you should be, oriented perfectly toward rest, aligned with the natural rhythms of breath and heartbeat, held in place by forces deeper than magnetism, more reliable than satellites, more ancient than stars. Close your eyes and drift, directionless and free, floating in the vast ocean of sleep. As the 21st century progresses, our relationship with navigation and orientation continues to evolve in unexpected ways. Modern smartphone technology has placed navigation capabilities in billions of pockets worldwide, making the question, "Where am I?" almost trivially easy to answer. But researchers have discovered something troubling about this convenience. Our brain's navigation abilities may be atrophying from disuse. Studies comparing London taxi drivers, who must memorize the city's intricate street layout in a training process called the knowledge, with ordinary drivers who rely on GPS, have shown that the taxi drivers develop enlarged hippocampi, the brain region crucial for spatial memory and navigation. The brain, it seems, is like a muscle. Navigation skills strengthen with practice and weaken without it. Neuroscientists studying how the brain creates our sense of direction and location have made extraordinary discoveries in recent decades. In 2005, researchers identified grid cells in rats' brains, neurons that fire in a hexagonal pattern as the animal moves through space, essentially creating an internal coordinate system. Combined with previously discovered place cells that activate when an animal is in a specific location, and head direction cells that track which way the animal is facing, these neural systems create an internal map and compass within the brain itself. This research, which won the Nobel Prize in Physiology or Medicine in 2014, revealed that our sense of location and direction isn't just a mental construct but has specific, identifiable neural architecture. Your brain contains its own navigation system, independent of any external compass or GPS, though far less precise. This internal navigation system isn't just for physical space. Remarkably, researchers have found that the same neural networks used for spatial navigation also activate when we navigate through abstract spaces, moving through memories, planning future actions, or even navigating social hierarchies. The hippocampus, crucial for forming spatial maps, is equally important for episodic memory, for placing events in time and context. The language we use reflects this deep connection. We speak of navigating relationships, of moving forward in our careers, of finding our way through difficult decisions. These aren't mere metaphors. Our brains actually use similar neural machinery for physical and conceptual navigation. The compass, in a sense, is built into the very structure of consciousness itself. Meanwhile, in the practical world of navigation, new challenges were emerging that old compass technology couldn't address. The Arctic and Antarctic regions, crucial for shipping routes and resource exploration as climate change opened previously icebound passages, posed unique problems for magnetic compasses. As you approach the magnetic poles, compass needles become increasingly unreliable, dipping at steep angles and swinging erratically. The magnetic North Pole itself, remember, isn't at the geographic North Pole but in northern Canada, and it's constantly moving. Since continuous tracking began in the early 19th century, the magnetic North Pole has wandered over 1,400 miles, and its movement has accelerated dramatically in recent decades, shifting at speeds of up to 34 miles per year. This accelerating drift of the magnetic pole has practical consequences. Aviation maps must be regularly updated to show current magnetic declination, the angle between true north and magnetic north. Airport runways are numbered based on their magnetic heading, and several airports around the world have had to renumber their runways as magnetic north shifted enough to change the heading by more than a few degrees. In 2011, Tampa International Airport in Florida had to close its primary runway to repaint the numbers. What was runway 1836 became 191 because magnetic north had moved. This seemingly trivial change required updating countless charts, procedures, and navigation databases, a reminder that even in the GPS era, we remain connected to Earth's wandering magnetic field. Scientists studying this accelerated movement have discovered that it's caused by changes in the flow of molten iron deep in Earth's outer core, about 1,800 miles beneath the surface. Two massive lobes of magnetic field, one under Canada and one under Siberia, have been competing for dominance, with the Siberian lobe growing stronger and pulling the magnetic North Pole westward across the Arctic. This is happening because of complex fluid dynamics in the outer core. Imagine vast rivers of molten metal, each one larger than the Amazon, swirling and eddying in the darkness beneath our feet, and you begin to sense the scale of the forces involved. These movements may be early signs of a coming geomagnetic reversal, though predicting such events remains beyond our current scientific capabilities. The prospect of a geomagnetic reversal, while fascinating to scientists, would pose serious challenges for modern technological civilization. During the transition period, which could last thousands of years, Earth's magnetic field would weaken significantly, potentially dropping to only 10% of its current strength. This field serves as a shield, deflecting charged particles from the solar wind that would otherwise strip away our atmosphere and bombard the surface with radiation. A weakened magnetic field would mean increased radiation exposure for astronauts, airline crews, and even people living at high altitudes. Satellites might suffer increased damage from solar storms. The spectacular auroras, northern and southern lights, caused by charged particles following magnetic field lines toward the poles, would appear at much lower latitudes, potentially visible from the equator. More immediately concerning for navigation, a weakened and chaotic magnetic field would make compasses increasingly unreliable. Multiple magnetic poles might appear temporarily in different locations. Compasses in different parts of the world might point in wildly different directions. This is where our redundant navigation systems, GPS, inertial navigation, celestial navigation, become crucial. We've built a civilization that depends on knowing where we are and where we're going, and we've wisely created multiple, independent methods for determining position and direction. The magnetic compass, that ancient device, might finally become obsolete not through technological replacement but through the failure of the very planetary phenomenon it measures. Yet there's something poignant about imagining a world where magnetic compasses no longer work, where that simple, elegant technology that served humanity so faithfully for nearly a millennium finally reaches the end of its usefulness. The compass represented a partnership with nature, a way of reading forces invisible to our senses but fundamental to our planet. Its potential obsolescence reminds us that even the most seemingly permanent features of our world, Earth's magnetic field, stable climate, reliable seasons, are actually dynamic and temporary. Nothing lasts forever, not even the directions we rely on to find our way. Perhaps this is the compass's final lesson, that orientation and direction are not absolute but contextual, not permanent but provisional. The compass needle points north only because Earth's magnetic field currently generates a north pole. That pole moves, wanders, and will someday reverse. The stars that ancient navigators used for celestial navigation are themselves moving through the galaxy, slowly changing position over millennia. Even GPS satellites drift in their orbits and require constant adjustment. All our reference points are temporary. All our maps must eventually be redrawn. And yet, somehow, life continues, navigation persists, and we find our way. There's a freedom in this realization. If all directions are temporary, if all reference points eventually shift, then perhaps we need not cling so tightly to the particular coordinates we've chosen, the specific headings we've set. We can adjust, recalibrate, find new reference points as old ones fade. The essential skill isn't maintaining a fixed course, but knowing how to orient ourselves anew when the world shifts beneath us, as it inevitably will. The compass doesn't teach us to reach a destination, but to continually find direction, to align ourselves moment by moment with the forces and fields available to us, to navigate through uncertainty with confidence that we can always determine where we are, even when where we are keeps changing. Rest now in this understanding. You are not lost, even if all the compasses spin. You are not directionless, even when north becomes south and east becomes west. Within you are older navigation systems than magnetism, deeper reference points than satellites, more reliable guides than any instrument. Trust the internal compass that has guided humanity through ice ages and climate shifts, through migrations and wanderings across continents, through all the changes that have come before and all those yet to come. Breathe slowly and feel yourself held, oriented not by external forces but by something essential within, something that knows the way even when the way is unclear. Let yourself drift now, safely guided into the realm of dreams, where direction has no meaning and all ways lead home. As we near the end of our journey through the history of the compass, it's worth exploring some of the more unusual and specialized compasses that have been developed for specific purposes, each one revealing something about human ingenuity and our endless quest to orient ourselves in challenging environments. One of the most fascinating is the sun compass, developed independently by several cultures but perfected in modern times for polar exploration. When magnetic compasses become unreliable near the poles, a sun compass uses the sun's position and the time of day to determine direction. This might seem straightforward, but it requires precise knowledge of your latitude and the date, along with complex mathematical calculations to account for the sun's changing path across the sky throughout the year. The sun compass became essential for polar aviation in the early 20th century. Pilots flying transpolar routes discovered that their magnetic compasses would spin uselessly or point downward toward the magnetic pole rather than horizontally toward magnetic north. In the 1920s and 1930s, before reliable gyrocompasses were available for aircraft, pilots used sun compasses consisting of a horizontal dial marked with our lines and a vertical pin that cast a shadow. By aligning the shadow with the correct hour line for their longitude and the current time, pilots could determine true north. This required constant adjustment as the aircraft moved and the sun's position changed, making polar navigation an exercise in continuous calculation. These early transpolar flights were as much about navigation skill as flying ability. A pilot might successfully cross the Arctic only to become hopelessly lost if their sun compass failed or clouds obscured the sun. Another specialized compass emerged from the unique needs of miners working deep underground, where magnetic compasses often behaved erratically due to local concentrations of magnetic ores. The Gruben compass, or mine compass, used a different principle entirely. Instead of magnetic north, it established an arbitrary reference direction, typically the direction of the mine entrance, and all subsequent measurements were made relative to this chosen baseline. Miners would carefully survey each tunnel and shaft, measuring angles and distances relative to the established reference. This approach worked regardless of magnetic interference, though it required meticulous record-keeping and surveying. A single error in measurement could propagate through the entire system, potentially causing miners to miscalculate their position by hundreds of feet. Despite this risk, mine compasses allowed the creation of accurate three-dimensional maps of underground tunnel systems, essential for safety and for connecting different parts of large mining operations. The military developed its own specialized compass variations, particularly the prismatic compass used extensively by artillery units and surveyors. This ingenious device combined a magnetic compass with a prism that allowed the user to read the bearing while simultaneously sighting a distant object through a vertical hairline. The prism reflected the compass card into the user's field of view, so you could look at a distant landmark and read its exact bearing at the same moment. British and Commonwealth armies particularly favored the prismatic compass, and it became standard equipment for officers. These compasses were built to withstand the rigors of combat, waterproof, shock-resistant, and designed to remain accurate even after being dropped, buried in mud, or subjected to the concussive forces near artillery fire. Perhaps the most elegantly simple specialized compass is the thumb compass used in the sport of orienteering, where participants navigate through wilderness terrain using only a map and compass. The thumb compass is worn on the thumb, leaving both hands free to manipulate the map, push through vegetation, or grab tree branches. Its dial is simplified to show only the essential information, the magnetic needle and a rotating bezel, because in orienteering, speed matters as much as accuracy. Competitors must make rapid navigation decisions while running at full speed through forests, and the thumb compass allows them to check their heading with barely a glance. This specialized tool reflects a deeper truth about navigation. Different contexts require different tools, and the best compass for one purpose may be poorly suited for another. The development of electronic compasses in the late 20th century represented another significant evolution. Unlike mechanical compasses with physical needles, electronic compasses use solid-state magnetometers, sensors that measure magnetic field strength and direction electronically. These devices, often called digital compasses or electronic compasses, have no moving parts to wear out, can be integrated into other electronic systems, and can provide bearing information directly to computers or autopilots. Modern smartphones contain three-axis magnetometers that measure Earth's magnetic field in 3 dimensions, allowing the phone to determine which direction it's pointing. This technology enables countless applications, from simple map orientation to augmented reality systems that overlay directional information on camera views of the real world. But electronic compasses introduced new challenges. They are susceptible to electromagnetic interference from other electronic devices, requiring careful calibration. The calibration process, often requiring you to wave your phone in a figure-8 pattern, is actually training the device to distinguish Earth's magnetic field from the local magnetic fields generated by the phone's own components. Electronic compasses also require power, unlike their mechanical ancestors that would work indefinitely with no energy source. In survival situations, a simple magnetic compass remains superior to an electronic one, because it will continue functioning long after batteries have died and electronic circuits have failed. The miniaturization of compass technology has reached extraordinary levels. Modern MEMS compasses, microelectromechanical systems, can fit on silicon chips smaller than a grain of rice. These tiny sensors are embedded in everything from fitness trackers to drone navigation systems to virtual reality headsets that track head orientation. The technology that once required a carefully balanced needle floating in liquid has been reduced to patterns of atoms etched on silicon, yet still measures the same fundamental phenomenon that Chinese navigators observed 1,000 years ago. This miniaturization has made direction sensing so ubiquitous that we barely notice it. Your phone knows which way you're facing. Your car knows which direction it's traveling. Your fitness watch tracks your heading during your morning run. Orientation has become ambient, woven invisibly into the technological fabric of modern life. Yet there's a paradox in this ubiquity. As compass technology has become more sophisticated, smaller, and more integrated into other devices, our conscious awareness of navigation and direction has diminished. People walking down streets stare at GPS maps showing their position as a blue, but have little sense of which direction they're actually facing or which way they need to go. They follow turn-by-turn directions without building mental maps of the areas they traverse. The compass, once a tool that enhanced spatial awareness by providing a reference point from which to build understanding, has been replaced by systems that eliminate the need for spatial awareness entirely. We know where we are, but we don't know the terrain. We reach destinations without learning routes. Some psychologists and neuroscientists worry about the cognitive consequences of this shift. Spatial navigation is one of the fundamental cognitive tasks that may have driven the evolution of intelligence itself. Many animals with sophisticated navigation abilities also display other forms of intelligence: tool use, social cooperation, problem-solving. The hippocampus, crucial for navigation, is also central to memory formation and recall. When we navigate actively, making decisions about direction and route, we engage cognitive systems that may be important for mental health and cognitive resilience. Studies have shown correlations between poor spatial navigation abilities and increased risk of Alzheimer's disease, though causation remains unclear. By outsourcing navigation entirely to technology, we may be neglecting an important form of cognitive exercise. This concern has sparked a small but growing movement to preserve and teach traditional navigation skills: map reading, compass use, dead reckoning, even celestial navigation. Organizations offer courses in these techniques, not because they're practically necessary in an age of GPS, but because they represent valuable knowledge and cognitive skills worth preserving. There's something deeply satisfying about orienting yourself using a simple compass, about building a mental map of terrain, about knowing where you are through your own observation and reasoning rather than through electronic intermediaries. It connects us to the long history of human navigation, to all those who found their way before satellites and electronics, who crossed oceans and continents with nothing but compasses, sextants, and skill. Let yourself settle now into this long history, this story of finding direction that stretches from ancient lodestone to silicon chips, from floating needles to quantum sensors, from the first cautious voyages out of sight of land to spacecraft navigating the solar system. You are part of this story, a descendant of navigators and wayfinders, carrying within you the cognitive capacity to orient yourself in space even when all your tools have failed. That capacity remains, dormant perhaps but not lost, ready to awaken when needed. Trust it now to guide you not through geographic space but through the landscape of sleep, finding the path that leads to rest, to dreams, to the deep renewal that comes when we surrender our need to know where we are and simply allow ourselves to be. Breathe slowly and drift, directionless and content, held safely in the vast field of night. As our journey through the history of the compass draws toward its close, we turn to some of the more philosophical and poetic dimensions of this simple yet profound instrument. Throughout history, the compass has served not just as a navigational tool but as a powerful metaphor in literature, art, and human thought. The image of the compass needle, eternally seeking north, has symbolized constancy, faithfulness, and the search for truth. In John Donne's famous 17th-century poem A Valediction, forbidding morning, he compares separated lovers to the legs of a drafting compass. Though they move apart, they remain connected, and one always leans toward the other. The compass became a symbol of love that endures across distance, of connection that persists despite separation. This metaphorical power of the compass extends across cultures. In Chinese philosophy and feng shui, the compass, called a luopan, is far more than a navigation tool. Traditional Chinese compasses are elaborate instruments with multiple concentric rings containing information about astronomy, calendar systems, the elements, and spiritual forces. A feng shui compass might have 20 or more rings of information surrounding the magnetic needle at its center. These compasses were used to orient buildings, temples, and graves in harmony with cosmic forces, aligning human structures with the invisible energies that practitioners believed flowed through the landscape. The compass became a tool for navigating not just physical space but metaphysical reality, for finding one's place not just on Earth but in the cosmos. The compass also played an unexpected role in the history of art. In the Renaissance, as European explorers were using compasses to navigate to distant lands, artists were using compasses, the drawing kind, with 2 legs and a pivot, to construct geometrically perfect circles and arcs in their paintings and architectural designs. But more metaphorically, the magnetic compass influenced art by expanding the world artists could depict. Before the age of exploration, European artists painted familiar landscapes and known territories. The compass enabled voyages that brought back reports of exotic lands, strange peoples, and unfamiliar flora and fauna. World maps expanded dramatically, filled with newly charted territories. This expansion of geographic knowledge expanded artistic imagination too, giving painters and writers new subjects, new perspectives, and ultimately contributing to shifts in how Europeans understood their place in a suddenly larger and more diverse world in the 19th century. As industrialization accelerated and cities grew, the compass took on new symbolic meaning, representing nature, authenticity, and connection to Earth in contrast to the artificial urban environment. Romantic poets and writers celebrated wilderness exploration, and the compass became an emblem of adventure and escape from civilization. This symbolism persists today in the iconography of outdoor recreation. Hiking guides, camping equipment, and adventure tourism all prominently feature compass imagery, even though modern hikers typically navigate with GPS. The compass symbolizes something beyond mere direction finding. It represents self-reliance, connection to nature, and a kind of authenticity that resonates with people who spend most of their lives in climate-controlled buildings navigating by street signs and GPS. The compass has also appeared in unexpected places in scientific history, sometimes illuminating phenomena far beyond navigation. In the 1820s, Danish physicist Hans Christian Ørsted was demonstrating electrical circuits to students when he noticed something remarkable. When electric current flowed through a wire near a compass, the needle deflected. This was the first demonstration that electricity and magnetism were related phenomena, a discovery that would lead to the development of electromagnetism, one of the fundamental forces of physics. Ørsted's observation, made possible only because he happened to have a compass near his electrical apparatus, eventually enabled the development of electric motors, generators, and transformers, technologies that underpin modern civilization. The humble compass, simply by being present in the right place at the right moment, helped unlock one of nature's deepest secrets. Throughout the 20th century, as compass technology became increasingly sophisticated, artists and designers began to appreciate the aesthetic beauty of compasses themselves. Vintage ship compasses, with their brass housings and gimbaled mounts, became collectible objects, displayed as sculpture rather than used as tools. The circular geometry of the compass rose, with its radiating lines and cardinal points, influenced graphic design and became a popular motif in everything from corporate logos to decorative arts. There's something visually satisfying about the compass's radial symmetry, its suggestion of all directions emanating from a central point, its balance between complexity and clarity. The compass rose appears on maps not just for practical orientation, but because it's beautiful, because it satisfies some aesthetic sense that geometric order has its own inherent rightness. The digital age has brought yet another transformation in how we interact with compass information. Modern mapping applications display a small compass rose in the corner of the screen, often animated to show current heading. But this representation is fundamentally different from looking at a physical compass. A physical compass exists in the same space you occupy. You and the compass are both in the world together, both responding to the same magnetic field. A digital compass is a representation, a symbol on a screen that stands for direction but doesn't directly embody it. This abstraction, like so many digital abstractions, is convenient and functional but lacks the tangible, embodied quality of older technologies. You can feel a physical compass in your hand, Watch the needle swing and settle. Observe the trembling hesitation as it seeks magnetic north. These tactile and visual experiences create a different relationship with orientation than simply glancing at an arrow on a screen. Some philosophers and historians of technology argue that this shift from physical to digital compasses represents a broader pattern in how we relate to the world. Physical tools like compasses, sextants, and chronometers required skill to use and created embodied knowledge. You learned navigation through your body, through the practice of taking sightings and plotting courses, through the physical manipulation of instruments. Digital systems require less skill and create abstract knowledge. You learn to follow directions displayed on a screen, but you don't necessarily develop deep spatial understanding. Neither approach is inherently superior, but they represent different ways of being in the world, different relationships between human and environment, tool and user, knowledge and understanding. As we approach the end of this story, it's worth reflecting on what the compass has taught humanity across the 1,000 years since its invention. At the most basic level, it taught us that invisible forces exist and can be harnessed, that nature contains subtle phenomena waiting to be discovered and used. It taught us that with the right tools, we could venture into unknown spaces with confidence, that the world was navigable, knowable, and ultimately less fearsome than it appeared. The compass was one of the technologies that enabled the age of exploration, with all its consequences both magnificent and terrible. The connecting of previously isolated peoples, the exchange of crops and technologies, but also colonization, exploitation, and the devastation of indigenous cultures. The compass is not morally neutral. Like all powerful technologies, it amplified human capabilities for both good and ill. But perhaps the compass's deepest lesson is about reference points and orientation. The compass works because Earth itself is magnetic, because our planet generates a field that extends from core to atmosphere, enveloping everything. We are all held within this field, whether we sense it or not, whether we acknowledge it or not. The compass simply makes visible what was always present, turns the invisible into the measurable, transforms a planetary phenomenon into a practical tool. In a sense, the compass is a teacher, showing us that orientation requires reference points, that to know where we're going we must first know where we are, that direction is not absolute but relational. North only has meaning because it's the opposite of south, because it's perpendicular to east and west, because it's defined within a system of relationships. This relational quality of direction mirrors something essential about human existence. We orient ourselves not just geographically but socially, emotionally, and spiritually through relationships and connections. We find meaning not in isolation but through our place in larger systems, families, communities, cultures, ecosystems, the planet itself. The compass needle pointing north is held in relationship with Earth's magnetic field, just as we are held in relationship with the countless visible and invisible forces that shape our lives. And just as the compass needle trembles and wavers before settling into alignment, so too do we move through uncertainty before finding our direction, provisional though it may be. In this moment, as you rest, you need no compass to tell you where you are. You are here, now, present in this single point in space and time. All the directions radiate from this place where you lie, breathing slowly, feeling the weight of your body against the surface beneath you. North and south, east and west, up and down, all of these directions exist, but for now they don't matter. You have arrived at the still center where the compass needle pivots, the quiet point around which all directions arrange themselves. Rest in this center, this calm, this perfect orientation that requires no movement, no seeking, no journey. You are already where you need to be. Close your eyes and let the world turn around you, held safely in fields you cannot see but which support you nevertheless, guided towards sleep by forces as reliable as magnetism. as ancient as Earth itself, as gentle as the needle finding north. The compass needle always finds north, but you need find nothing. The searching is over. The navigation complete. You have arrived at the destination that was always waiting for you. This moment of perfect rest, this harbor of sleep where no bearings need be taken, no course needs plotting.